Dear students, after studying this module, you shall be able to know about the basic underlying principle of the Curtn-hammett principle. Understand the energetics involved in the Curtn-hammett principle and learn about the various case studies of this principle. Analyze the derivation of the Curtn-hammett principle and what are the implications of the same. Study of the various kind of examples based on this principle. In a chemical reaction which yields a product X from a conformational isomer A dash and also yields a different product Y from another conformational isomer A double dash, provided these two isomers are rapidly interconvertible relative to the rate of formation of products, whereas the products do not undergo interconversion. The product composition is not in the direct proportion to the relative concentrations of the conformational isomers in the substrate. It is controlled only by the difference in the standard free energies, that is delta G of the respective transition states, as shown here in the given reaction. The reaction scheme for the comprehending the Curtn-hammett principle indicates that how A dash is interconvertible to A double dash by the reversible reaction, whereas A dash gets converted to X and A double dash converted to Y with the rates of reaction shown by Kx and Ky. The relative concentration of the conformational isomers A dash and A double dash is obviously related to the product composition, that is conformational equilibrium constant at the respective rate constants of their reactions. Various parameters such as these are generally, though not invariably, unknown. The diagram represents the energetic situation for the transformation of interconverting isomers A and A dash into products X and Y. In this module, we focus our attention on understanding the basis of the Curtn-hammett principle and its intricacies. The energy diagram for the standard molar free energy and for the formation of the different products from A dash are shown here. Curtn-hammett principle. If the rates of reactions are much slower than the rate of interconversion, the Curtn-hammett principle states that the product distribution is controlled by the difference in the standard Gibbs energies of the respective transition states. In a more specific statement, if both the conformers react at the same rate, the product distribution will be the same as the ratio of the conformers at the equilibrium state. If the major conformer B is the faster reacting conformer, the product Pb will be formed predominantly and the ratio will not reflect the equilibrium distribution. If the minor conformer A is the faster reacting conformer, the product ratio will depend on all the three variables K1, K2 and K equilibrium, and the observed product distribution will not reflect the equilibrium distribution. Accordingly, the product formed can potentially derive from the conformer that you cannot even observe in the equilibrium distribution of the precursor. We shall now take up specific cases relating to the Curtn-hammett principle. These cases take up the various Curtn-hammett conditions in which the isomers react to give the particular products. Case 1. When the major product is obtained from the less stable conformer. If the rate of conversion of either of the two conformers is faster than the reaction rates, conversely, if the rates of reactions are much slower than the rate of interconversion, that is delta G AB is much small relative to delta G1 and delta G2, then the ratio of A and B is constant throughout the course of reaction. This is depicted by the energy diagram in the figure, where K1, K2 is much smaller than Ka and B. A to B are interconverted, whereas A to Pa is a slow reaction, while B to Pb is a not that slow a reaction. When the less stable isomer leads to the formation of the major product, this is how the energy diagram will be shown. Case 2. When the minor product is obtained from the less stable conformer, the energy diagram is again shown here, where the product Pa is the minor one and product Pb is the major, and the relative energy graphs are shown. Deriving a mathematical relationship based on the Curtn-hammett principle. Using the rate equations of the differential Pa by dt is equal to K1 into the concentration of the A, and differential of Pb by dt is equal to K2 into the concentration of B, we can write dPb by dPa is equal to K2 by K1 and multiplied with the concentration of B with divided by the concentration of A, or henceforth the dPb is equal to K2B by K1A into dPa. Since A and B are in equilibrium, we can substitute K equilibrium as the concentration of B to the concentration of A, and henceforth the equation further integrating, we get the relation as Pb by Pa equal to K2 by K1 into K equilibrium. In the situation here, A and B are in rapid equilibrium and we have to analyze the product ratio. We must consider the rates of reaction of the conformers as well as the equilibrium constant. To relate this quantity to the delta G, that is free energy values, recall that delta G is equal to minus RT natural log of K equilibrium, or K equilibrium is equal to e to the power of minus delta G by RT, where K1 is equal to e minus delta G to the power of divided by RT, and K2 is equal to minus delta G2 by RT. Substituting these two relations in the above equation, we would get the relation as Pb by Pa is equal to K2 by K1 into K equilibrium constant, which will be in turn further related to e to the power of minus delta G2 by RT, e to the power of minus delta G by RTE, and delta G1 divided by RT. Combining the following terms, we come to the final conclusion of the statement, where delta G is equal to delta G2 plus delta G naught minus delta G1. The implication of this derivation is the isolation of the product obtained from a conformer, which one can't even possibly observe even in the ground state. Within these limits, three scenarios can be envisioned. If the faster reacting conformer happens to be the major conformer, the product obtained from the major conformer should prevail and shall not reflect the equilibrium distribution. The product distribution will be the same as the ratio of the conformers at equilibrium if both the conformers react at the same rate. If the faster reacting conformer happens to be the minor conformer, then the product ratio will depend on all the three variables and the observed product distribution shall not reflect the equilibrium distribution. The case of non-equilibrating conformers. If the rate of interconversion happens to be slower than the rates of reaction, then course of the reaction and the product distribution, that is Pb by Pa shall simply reflect the initial equilibrium composition of A and B, cannot K1, K2 much greater than Ka and Kb equilibrate during the course of reaction. This is clearly depicted in the figure. Notice here that the rates of protonation observed are much faster than the rates of the conformer interconversion. Examples of Curtn-hammett relationship: diastereoselective quaternization of tertiary amines, alkylation of tropane. Quaternization of tropane occurs mainly from the less hindered pyrrolidine side equatorial attack at the piperidine ring, and even though the main conformer of tropane has an equatorial methyl group, notice that in this case the less stable conformer reacts much faster than the more stable conformer, resulting in an unexpected major product as shown in the depiction of the reaction. We can see here that the major product and the minor product are obtained through the fast and the slow reaction, where the reaction is monitored by carbon 13 method. Alkylation of 1-methyl 2-phenyl pyrrolidine. 1-methyl 2-phenyl pyrrolidine yields mainly an anti-alkylated product via alkylation of the minor cis conformer when treated with phenecyl bromide. In both the instances, the less stable conformer is more reactive to such an extent that the major product of the reaction results from this minor conformer. We can see here in the given figure the major product reacting with phenyl COCH2Br in the with a slow reaction, while minor reacts at the faster rate, and the products are minor and the major products are obtained in the ratio of 23:77. Oxidation of piperidines. Oxidation of 1-methyl 4-tertiary butyl piperidine yields mainly the amine N-oxide derived from the most stable conformer. In this example, the more energy rich, less stable conformer reacts more slowly than the major conformer, which is more stable and faster reacting. As it can be seen, the less stable conformer reacts slower, leading to the product which is a minor product, and the more stable leading to the major product, and both of them obtained in the ratio of 5:95. Asymmetric hydrogenation of prochiral olefins catalyzed by rhodium. The asymmetric hydrogenation of the prochiral olefins is a crucial catalytic process. This process involves the use of chiral ligand where two diastereomeric complexes can be formed. This is clearly depicted here in the figure. The two diastereomeric complexes are formed when a chiral ligand is used, as can be seen in the figure. Also, the observed enantiomer is obtained from the minor complex and the major complex. In the absence of the hydrogen, complex 2 is observed as the only diastereomer for the catalyst substrate complex. Further, the enantiomer selectivity depends strongly on the pressure of the hydrogen, and at high pressures of hydrogen it degrades rapidly. Enantiomer selective lithiation. In this reaction, it has been observed that regardless of the fact that the starting material is chiral, and even at low temperatures, enantiomer selectivities remain the same. This also suggests that the two alkyl lithium complexes must be in equilibrium. If the equilibrium conditions are not followed, then at a lower concentrations, enantiomer selectivity should be higher. This is an example of dynamic kinetic resolution in which, on reaction with the electrophile, the two enantiomeric lithium complexes are equilibrating during the course of reaction. Here it can be seen that Because the spartine is chiral, these two complexes are diastereomeric and have different properties. As we can see, the products are obtained in the two different concentrations. In order to summarize and conclude, the Curtn-hammett principle basically states that relative amounts of the product obtained from the two interconverting conformers depend on their reactivity if their interconversion is rapid. On the contrary, the relative amounts cannot always be intuitively predicted. Let's summarize this module. We have taught you that in 1940s the idea was prevalent among the chemists that the conformation of a reactant could be determined from the structure of a reaction product. That is, the major conformer would yield the major product. This assumption was shown to be incorrect by Curtn and Hammett in 1950s. If the rates of reactions are much slower than the rate of interconversion, the Curtn-hammett principle states that the product distribution is controlled by the difference in standard Gibbs energies of the respective transition states. The cases taken up in this module cover the various Curtn-hammett conditions in which the isomers react to give the particular products. Various examples of the Curtn-hammett principle have been taken in order to understand the principle and its variation in the better way. The Curtn-hammett principle basically states that the relative amounts of the products obtained from the two interconverting conformers depend on their reactivity if their interconversion is rapid. On the contrary, the relative amounts cannot always be intuitively predicted.